So in this video, we're going to take a look at how we can apply Pythagoras' theorem and trigonometry in 3 dimensions. Let's get stuck into this example. So a box has the dimensions shown in that diagram. A game is to be packed into the box. Part of the game is a rod that will just fit into the box. Find the length of this rod. Now, the best way of packing a long item into the box is to go from opposite corner to opposite corner. So imagine the rod being that blue line there. If we could find that length, then that would be the maximum size of the rod, right? Okay, but unfortunately, things are not straightforward because that is part of a triangle, I guess, or we could maybe use Pythagoras there. So we would have one side length, look, between C to G, but unfortunately, the other side is diagonally across the bottom there. Now that is a right angle, so we could use Pythagoras, but we'd have to find A to C first, and we don't have that information. However, we can find it because if we think about, forgive my poor drawing here, look, okay, if we think about a triangle that goes from A to B to C, look, along that line, okay, we could find that hypotenuse from A to C. Let's think about that, look, okay, again, maybe we could redraw it here, look, okay, there's A, there's B, there's C, that would be 40, that would be 80. So if I want to find that length from A to C, I could do so using Pythagoras. A to C squared would be A to B squared plus B to C squared. And I have some of this information. I've got to do 40 squared plus 80 squared. Well, that would be 8,000. And so therefore A to C is the square root of 8,000. Now, I don't want to round that at this point because I don't want to get a rounding error later on. I've got to do some more calculations yet, but we've got A to C. Okay, now we can start thinking about that blue triangle and finding the length of that rod. So if I'm now going to draw that blue triangle, well, I can use my calculation I've just found for A to C to help me to do that, right? Because A to C, we've just worked out, is the square root of 8,000. We know that C to G is given to us. That's 60 centimeters there. So we can use Pythagoras again now to see if we can work out the maximum length of that rod, which is the length from A to G. So again, AG squared is going to be AC squared plus CG squared. If I sub in the numbers, I'm going to have 8,000 plus whatever 60 squared is. Well, I can work that out. That comes out to be 11,600. So if I square root that, AG is the square root, look, of 11,600, which is approximately, and let's use the correct terminology, approximately 107.7 centimeters. Okay, so what do we have to do? Well, we used Pythagoras twice there, so we could find the diagonal, first of all, using another diagonal. Right, let's take a look at a second example. Okay, so a pyramid is made up of a square and 4 equilateral triangles with side length 10 centimeters. Find the height of the pyramid. Okay, well, let's have a little think about how we could do this. So first of all, maybe we could construct again a triangle that we could use to help us find the height, look, from E to X of that pyramid. So if I'm trying to find that height there, that length, maybe if I continue to draw in this way, I could think about a triangle there, look. Okay, now I have one of those already, don't I? I have D to E. The length of the sides of each equilateral triangle is 10 centimeters. So certainly I could write in 10 centimeters there. Now let's draw that. We might have to come back to this in a moment, right? We've got X in the corner, which we know is at a right angle because we're looking for that height. We've got D there and E there, and we know that's 10. Now, what we could do with finding out first is that length there, look, from D to X. So let's think then about the base of that, right? Okay, and maybe we could figure out first all the way across, look, from D to B. Now, that might be worth doing because if I was to draw that triangle out flat, look, let's think about it as a flat triangle, C being there and B being there and D being there, well, that 90 degrees corresponds to that 90 degrees there. I have some of these lengths. I have that they're both 10 centimeters because they're the sides of those equilateral triangles. So if I'm now trying to find the length of B to D, well, I know that I can use Pythagoras. B to D squared is going to be D to C squared plus B to C squared. Putting those numbers in, that's 10 squared plus 10 squared. So we're going to have 200 there. So B to D is going to be the square root of 200. Now, I don't want all the way across from there, look, okay? What I want is I only want half of that distance. I want to find it from D to X. So I could write that, well, D to X is half of B to D, which is square root of 200 divided by 2. Now, if I don't have a calculator to work some of this stuff out, but maybe I do, maybe I don't, I could just work that as a decimal. But do you know what? I'll save a little bit of time and be clever about this. Let's write this as the square root of 200 over the square root of 4, because 2 is the square root of 4. And from there, I can actually write down that that was the square root of 50. Okay, so let's put that back into the other blue triangle that we were thinking about earlier. From D to X, we've got the square root of 50. Okay, now, from here, we can now work out the height that we're trying to find, because I could say that e to x squared is going to be d to e squared, take away d to x squared. And we have all the information that's going to help us to work that out. Okay, so that is going to be 10 squared, take away the root of 50 squared. So that's a bit like saying, well, 100 minus 50, which is 50. So that means that e to x itself is the square root of 50, and that is approximately 7.07 centimeters. So the height of that pyramid is 7.07 centimeters. Okay, final example. Now let's put some trigonometry into this one. This is a very tricky little question, so let's be very careful about this. So we've got a carpenter is to cut an isosceles triangle out of a sheet of wood. The triangle is to fit in the corner as shown in the diagram. Right, we've got some length given to us as well. O to A is the same as O to C, which is 5 centimeters. I'll write those 5s in there, look. And then we've got O up to B is 20 centimeters. Find the size of each angle in the triangle. Okay, well, we can have a little think about this. Let's use our colors again. Let's imagine we've got this red triangle I've written from A to O to B. It's actually going to be the same red triangle, isn't it? Okay, with the same dimensions as from O to B to C. So if I use that first idea there, A to O to B, we can put some values in, certainly, because we know that we've got 20 centimeters from O up to B. That's given in the question, and 5 centimeters from A to O. So if I wanted to use that, find that length from A to B, I could use Pythagoras to do that. AB will be the square root of 20 squared plus 5 squared, which is the square root of 425. Okay. And of course, I know that that is the same thing as B to C, because that triangle is exactly the same. So AB and BC are going to be the square root of 425. Now, another triangle we might want is the lower triangle there, look. Okay, that's flat against the floor. We could think about that triangle as well quite easily because we have 2 lengths. We know that between that right angle, we have 5s from O, through to A and from O to C. So if I wanted to think about AC, well, AC would be 5 squared plus 5 squared square rooted. And again, it's our favorite number of the video. It is going to be square root 50. So now I've got all those values. Now I can start to think about the isosceles triangle that we've got in our question, right? Imagine if we now draw from A to B to C. We've got everything we need, right? So let's draw from A to B to C. We worked out that A to B was the square root of 425. That was the same as B to C because this system is symmetrical. That's also 425. And we also worked out that A to C was the square root of 50. Right, now let's go back. We have to find out each angle in this triangle. So let's just use theta to represent angle for a second. Let's start off with that angle there, A, because if we can find that one, well, this is an isosceles triangle. It's going to be the same as that angle there at C. Now, using simple right angle trigonometry, we would need to split this in half. So let's do that. Let's take the left-hand side of this and redraw that. Okay, we've got a theta there. We've still got that length of 425, but we've got half the distance. We've got root 50 divided by 2. Now we can use simple trigonometry to help us to work this out. We've got the adjacent side to the angle. We've got the hypotenuse to the angle. So that means that we can use the cosine ratio to help us. Cosine of theta would be root 50 over 2. That's the adjacent, divided by the hypotenuse, which is 425. So if you do a cosine minus 1 on your calculator and type in root 50 over 2 divided by the square root of 425, we're going to get 80.1 rounded to 3 significant figures. So from B to A to C, which is the same as from A to C to B, we have them both coming out at 80.1 degrees. Now, we've found 2 out of 3. We can find the angle at B very easily because it's a triangle. We can take both of those angles away from 180 to find that. So 180, take away 80.1, take away another 80.1, comes out at 19.8 degrees. So our final angle we need to work out, which is up there, look at B, A to B to C, is 19.8 degrees, and we have all 3 angles. Okay, I hope this gives you some good examples of how you can use your trigonometry and Pythagoras' theorem in 3 dimensions.